let's label some axes here. I want to kind of model what your Q table looks like in some respects. Let's suppose this is a pole angle, right? Do you agree with me that, and let's put happiness or value. Basically, if the pole angle is too low, your happiness is pretty bad. If the pole angle is too high, your happiness is pretty bad. If the pole angle is somewhere in the middle, your happiness is pretty good, right? So I don't know the exact shape of this thing internally, but it's probably one of those-ish, right? Except for that dip right there. That's a bad spot in my Q table where it hasn't fully converged. But as we're building this thing, it probably goes through many phases where for a while it looks like this, right? And it takes a whole lot of pounding on this neural network before it gets to this nice curvy hill. And once it gets to this nice curvy hill, you're kind of in this state where if you're right here and you say, oh, the pole angle is too far that way, you realize if you go to the right, you're going to be happier. If you go to the left, you're going to be less happy. And so you go to the right, and basically you end up achieving sort of homeostasis, right? But you agree with me, it's not quite that simple because pole angle isn't the only consideration. If your pole is completely vertical, but your angular velocity is super, super high, although you're happy at the moment, you're just about to be sad, right? And so it realizes, hey, we need to compensate for that and try to get the angular velocity small. So let's add a new axis here. Now I'm just going to wave my hands because I can't draw it. But there's an axis coming out here of angular velocity. And if you have too much angular velocity or too little, or too positive or too negative, that's usually bad. Although it depends on the pole angle. So maybe it's not a perfect hill. Maybe it's kind of a warpy hill, kind of a twisty spiral or something. But there's a point on it that's higher than everywhere else. Okay? And now let's make the game more complicated. Let's suppose that instead of just being able to move the cart to the right or the left, maybe you could also move the cart in or out. Maybe we're in a 2D plane now. So now you've got more actions you can do. At some point we can't really visualize this anymore, but there's still this concept of somewhere that you want to be, and the closer you are to that point, the happier you are, and the farther you are from that point, the sadder you are, right? Okay. Do you see that that kind of provides a general, here I'll try to draw 3D-esque thing. That feels 3D, doesn't it? Okay. Now we've got a 3D picture. I guess I need the axis too. There. Now it feels like in 3D space, we're always trying to climb up that hill. Here's why I think that's at least semi-plausible for real life. So I have a job, and why did I show up to class today? Because in 2 weeks I'm going to get a paycheck, and when I do I'll be happy, right? That's basically my reward. Although the funny thing is I don't sit around thinking about my paycheck all the time. I mean, at some point it kind of just, the paycheck comes in, and I'm not really going for the reward. I start falling into these habitual grooves. And really, I'm just always trying to stay on top of homeostasis in some respects. So let's suppose my students are angry at me. That kind of puts me in an unhappy mode. And I'm going to try to get back on top of the hill. But let's suppose not only are my students angry at me, but my lesson plan isn't yet produced, and there's a test coming up, and I haven't yet written it, and my boss wants me to prepare a seminar because he has some visitors coming to the department and wants me to present. Now I've got a lot of stuff I got to do, right? And how am I going to do it? Well, I'm going to kind of think what direction is going to get me most in control again. Maybe I better prep my lesson plan because class is in 20 minutes. So I get working on that. Or I think you get the point. Do you see that kind of the way we make decisions in life is we think about how far we are from being at peace, from being at this balance in our universe, and we think about what actions are going to lead us closer to the top of that hill, and that's kind of what we do. And almost, if humans are these future predicting machines where we sweep through our list of possible actions and say, okay, I could work on this, or I could work on that, or I could work on this other thing, we always choose the one that's going to move us closest to the top. And really, if we could just produce this model that somehow captures our priorities and what's important to us, that kind of tells us what to do at any point. If you're just trying to picture a life form, a simple life form, right? These axes might be, its temperature. Creatures don't like being frozen to death, and they also don't like cooking in an oven. There's some happy medium along the temperature axis. They don't like having their tummies be totally empty. They don't like having their tummies so crammed full that they're ripping apart and blood is oozing out. They like just being nice, pleasantly full of food, right? And so there's some kind of hill in this multi-dimensional space that everything's trying to balance all the different aspects of its state, and they make whatever actions, whatever decisions lead to maintaining happiness or peace or value or homeostasis or whatever you want to call it.
So is peace and happiness always an unstable equilibrium?
Well, if you live in a dynamic world, probably. As long as I keep putting food in my tummy, it keeps turning into excrement, which I don't like, and I want to get that out. But I don't want to do that in public, and lots of other things, and there's all kinds of social complexities about the whole matter, and well, I'm not going to continue lecturing about poo. But, but yeah, the point is, time really has a crazy effect on all of this. But can you see that the idea of a Q table, modeling your priorities and values, and you always seeking homeostasis, I'm not claiming you have a Bellman equation in your head, but I am claiming we don't keep our eye focused at all times on getting rewards. We do have kind of this concept of being close to our rewards and being far away from it, and we do kind of gravitate towards getting this steady stream of rewards and staying away from these penalties of badness in our lives. I'm trying to argue that it's at least somewhat biologically plausible, this whole concept of a Q table. Okay, so how do we represent our values? There's kind of three main camps. So you can say that action is a policy of state. I'm going to use A for action. Okay, A equals action, X equals state, V equals happiness, value, utility. Not quite reward, because anticipation of a reward is more what we're associating with value, at least according to the Bellman equation. And yeah, at most we approximate a Bellman equation in our heads, if we even do that. Okay, I'm going to say P here is a policy function. A policy maps from state to action, as indicated by that equation. You with me? Okay. So if what you do is based on your state, then you've got a policy. If you say your happiness is based on, a value function of your state, I'm going to change this to U, and we'll go with utility, just so I can not have so many clashes in my variables. So you're going there, and you're going to go here. Okay, we can say utility is a function of our state, or we could say quality, which is also kind of utility, is, let's go, utility is a function of state and action. Right? Now, this is the one we have studied. We have been saying that, hey, if you know where you are and what you're going to do, that leads to overall utility, happiness, value, homeostasis, whatever you want to call it. Yeah. Okay. What I'm suggesting is there are three ways of looking at it, and they're all kind of the same way, so you don't even have to think of these as different. But I'm going to give them all names. This is called a policy. This is called value. And this is called Q table. The idea being that a Q table maps from state and action to utility, or happiness, or contentment, or whatever you prefer. A value table maps from the state you're in to the utility, and a policy doesn't even consider the concept of utility. It just says, if you're in this state, here's what you should do. So you could think of the policy people as being of the opinion that humans don't really think about what they're doing, they just act according to their state in life, right? Action is this function of state, and then maybe they derive their happiness based on what's going on. The value people would say, no, we think about how happy we are in each state, and we try to get to states that make us more happy. And the Q table people kind of mix it a little bit and say, no, we think about what state we're in and what actions are going to lead to the better utility, and then we do that action. You see that you can think of that, of being an agent in all of these different modes, right? Okay, well, turns out all of these are types of reinforcement learning models, and you can make reinforcement learning work with any of these approaches, any of these methods. So if you take, for example, a value table, and let's do our simple grid world game. So we have a grid world, and you say, what's the value of being in any state? And we say, well, this state has a value of 5, and maybe these have 4s. And this one's a 3, and this one's a 3, and this is a 2, and that's a 2, and this is a 1. That kind of suggests you should try to go from the bottom left corner up to the top right corner, right? Because you're seeking greater value. If we use some equation and we say each state is a function of the states adjacent to it, according to what action you do, we can iterate on the values and get a table that converges. This is called value iteration. When you iterate values until it converges, you've done value iteration, which is a type of reinforcement learning. You can also do that with a Q table, where instead of putting a value in each state, you put a value on each action from each state. That's the one we did. That's called Q iteration, I think. I've never actually seen that expression in the literature, but it should be, because then it would be consistent with the others. And you can also do something called policy iteration, which is where you don't even ever calculate a value. You just calculate what action you're going to do. And in each state, you could say, okay, I'm going to go from here to there, and I'm going to go from here to there, and from here to there. And you could keep switching your actions until they tend to lead to the goal better. And if you iterate on that over and over and over, it will converge to an optimal policy. So 3 different ways of doing reinforcement learning, and they can all work. Pretty much. Doesn't have to be. I guess the origin of reinforcement learning is you take a rat, you put it in a cage, you give it 2 buttons, it pushes this one, it gets some cheese, you push that one, it gets an electric shock, and then you notice, hey, it just keeps pushing the cheese button. Why? Oh, it must be smart. Yeah, this is suggesting that when you do reinforcement learning, if you iterate on one of these 3 concepts, it results in a model that allows you to seek better rewards. And so I'm just trying to point out there's at least 3 different types of reinforcement learning. There's probably even others, but these are the main 3. And then we're going to kind of talk about them a little so you have a good general overview of reinforcement learning. Alas, I am out of time, so I will say thanks for coming, and next time we'll talk some more.